All right, welcome back. Here we go with 1.6, other types of equations. That is a really big general thing. Things that apply though, no matter what you're working to solve. Don't forget what we've already learned. We focused in 1.5 on solving quadratic equations. Now we're going to be still solving equations, just of other types. Make sure that you're working to isolate the variable. You're solving to figure out what values for x will make your equation true. So you want to get x, that term with x by itself somewhere. We always want to solve using opposite or inverse operations. So for example, addition and subtraction are opposite operations. Multiplication and division are opposite operations. If I have something that's being squared, taking the square root of that thing. Those are opposite operations. So those are examples of opposite or inverse operations. My golden rule for math, doing to one side of the equation what you do into the other. So if you have x minus 7 equals 0, I'm going to solve that by adding 7 to both sides. If you have 7 times x equals 0, I'm going to solve that by dividing by 7 on both sides. So we always use those opposite or inverse operations to solve. Now, we're going to be focusing on how many types? 1, 2, 3, 4 basic types of other equations today. Don't get overwhelmed. Please stop, pause the video, take a break when you need to take a break, go back and rewind. If you don't think you got something, do these notes actively so that when you get to class, you will have already been through all the concepts. Now, radical equations, we want to isolate the radical. A radical is anything with a root. So an example of a radical is a square root, a cube root, a fourth root. My index goes up here, I-N-D-E-X. Index is this number in the little crook of the check mark. If it doesn't have a number in the index, it's a square root. If it's not a square root, we have a number there that represents our index. Once we've isolated that radical, that root, we undo it. We use our inverse operation. So if I've got the square root, then I need to square to solve. And usually in this course, that's what we're doing. If it were a cube root, we would have to cube to solve. If it were a fourth root, we would take both sides to the fourth power to solve. Whatever index we're trying to get rid of, we do that opposite thing to both sides. If I have more than one radical, I have to repeat that process. So I repeat if needed because I have more than one radical. We want to eliminate all the radicals in the problem. Then I simplify and solve. I have to remember though, anytime I square to solve, I have to check both solutions. Well, not checks, check both of the solutions. Because anytime I square to solve, I might have created what we call extraneous solutions. These are solutions that I introduce, but they don't actually work in the original equation. Anytime you square to solve. Now if you cube to solve, it's not a problem, but when I square to solve, I've messed up if I had a negative. So let's think about this. If I had -2 and I square it, I get a +4. If I have +2 and I square it, I get a +4. So if I take the square root of 4 to go backwards with that, square root 4, what does that equal? Well, it could equal a +2 or a -2, I don't know. Because that squared term, that if it started negative, that negative disappears. However, if I raise something to the third power to an odd exponent, a negative times a negative times a negative is still a negative. 2 times 2 times 4 is 8. That would be a -8. If it starts positive, it stays positive. If it starts negative, it stays negative if my exponent is odd. If my exponent is even, though, I have to worry about whether I mess that up. So if I square, raise it to an even power to solve, I might have created an extraneous solution. So let's take a look at that. We're going to do an example with just one radical so that we can get the down before we get too complex. My radical equation, we're going to use square root of x plus 3 is equal to x. My first step is to isolate the radical. Well, here's my radical. I need to get it on the same one side of the equation by itself, which means I need to move this 3 out of the way. Opposite operation, plus 3, the opposite is minus 3. So now I've got the square root of x plus 3 is equal to x minus 3. I have isolated the radical on one side of the equation. My next step is to square to solve. Now it's square root, the opposite of square root is to square, so I square both sides of the equation. That matters. I'm not squaring x separate from 3, I'm squaring x minus 3. Now over here on the left, I know that when I square a square root, that cancels out. Those are opposite or inverse operations. And so what I'm left with here is just x plus 3. But on the right, I need to multiply x minus 3 times x minus 3. And if you get in a hurry, this is where you'll make your mistake. Because if you think, oh, that's x squared, and then 3 squared is 9, so x squared and plus 9, or x squared minus 9, is going to give me, I'm sorry, that buzz, I had a phone call, that x squared minus 9, that leaves you with a missing middle term. So make sure that you go ahead and FOIL this. Either write it down, do it on the side, or remember your pattern. Your pattern for squaring a binomial is you multiply the first term times itself, so that's my x squared. I think about multiplying those two together twice. That's my negative 3x, so that gives me negative 6x. And then I square that second term. Negative 3 times negative 3 is a positive 9. All right, so I isolated my radical. I squared to both sides to solve. I don't need to repeat. Now I'm going to simplify. Well, when I take a look at this long list of terms, I see that this is quadratic because I've got a squared term. My first try for solving a quadratic, since I'm going to have a squared term and an x squared and a constant, or an x term and a constant, is going to be to set it equal to 0 and want to factor it. Now, my squared term is already positive, so I need to move everything to the other side to keep that squared term positive. I never want to try to factor with a negative squared term. I always want to factor with a positive squared term. So I move my x over, I move my 3 over using opposite operations. Now I've got my quadratic in general form set equal to 0, and I can reverse FOIL or factor to solve. X times x gives me x squared. I see that my signs are going to be the same because that's a positive constant. They're both going to be negative. So I have x minus, x minus. My factors of 6, I can multiply 1 times 6 or 2 times 3 to get 6. I need factors of 6 that are going to add up to give me 7. So it's going to be the 1 and 6 that I use this time. So x minus 1, x minus 6. Check my progress, make sure it works. Outside product is negative 6x, inside product is negative 1x. That gives me that negative 7x in the middle. Now I'm saying if I multiply both of these together and I get 0, then my zero factor property says that I set them each equal to 0 to see what would make that happen. Opposite operation, I get proposed solutions of 1 and 6. Now, I'm not done because I said that anytime you square to solve, you have to check for extraneous solutions. You have to check for extraneous solutions. I'm sorry, I went to grab another fun color and it's not working for me. Let me try again. Okay, so here's me checking for my extraneous solutions. The first solution I'm going to check is x equals 1. Excuse me, when I check it in the original equation. So, if x is 1, this is 1 plus 3 equals 1. And I already see I got a problem because that's already not going to work and that's going to add value. 1 plus 3 is 4, square root 4 is 2. And 2 plus 3 does not equal 1. So that's extraneous. That's not a valid solution. All right, let's check our other proposed solution, x equals 6. Side work I did. If x equals 6 in our original equation, 6 plus 3 equals 6. Well, 6 plus 3 is 9, so that's square root of 9. Square root of 9 is 3, and 3 plus 3 does, in fact, equal 6. So that's a valid solution. So my only solution, I found 2, but this one was extraneous, so this one is my only valid solution. Okay, rolling right along. Remember to pause if you need to pause. We're going to define an imaginary number. Now, imaginary does not mean useless. It means that when mathematicians rolled around and found square roots of negatives and it didn't fit in their real number system, they had to call it something, and they named it imaginary, and they did it a disservice because imaginary numbers are super useful in lots of places. We wouldn't have cell phone technology without imaginary numbers. My definition of an imaginary number is that my imaginary number, is equal to the square root of a negative 1. I is equal to the square root of a negative 1. Square root of a negative, not a real number. So if I have square root of a negative, I know it's imaginary. So let's look at this. If I do square root of 9, well, I know that that could have been 3 or negative 3, right? Primary or principal square root is 3, or negative 3, because 3 squared is 9, negative 3 squared is 9. But what if I have the square root of a negative 9? Well, there's no number times itself that gives me negative 9. So I have to think about this as a negative 1 times 9. And then I can evaluate those separately. Square root of a negative 1 times square root of 9. Well, square root of 9 is 3. We define square root of negative 1 as I. So the square root of negative 9 is 3i. Imaginary numbers give us non-real solutions. They don't show up on the graph. Now I can graph imaginary numbers, but I can't graph it on my real number coordinate plane. This little note here, let's work through this. Negative 1 times negative 1 is 1. 1 times 1 is also 1. So if I have x is the square root of negative 1, then x is equal to I, that imaginary number. Even roots have 2 possibilities, so we need to verify answers, because I could have started with a negative and squared it, I could have started with a positive and squared it, and ended up with the same value. So anytime I have even roots, there are 2 possibilities. We need to make sure we verify answers. Even roots are going to be things like square root, fourth root, sixth root, etc. Now, if I'm working with odds, negative 1 times negative 1 times negative 1 is still a negative 1. But if I start with positive 1, I get a positive 1 out. So if I have an odd exponent, if I start negative, I stay negative. If I start positive, I stay positive. So if I'm trying to solve for the cube root of a negative, well, that's a negative 1. Negative 1 times itself 3 times gives me a negative 1. So if I have odd roots, odd exponents, there's only one possibility, so we don't have to choose, which means we don't have to be stressed about extraneous solutions, and we don't have to go through the work of verifying our answers. All right, let's talk about our next type of equation, our equations with rational exponents. A rational exponent is a fraction. Now, if the index is even, remember, index is even, we're going to use plus or minus. Keep that in mind. Rational exponent is a fraction exponent. Now, just a reminder, when we are multiplying, when we are raising an exponent to another power, when we're raising an exponent to another power, I multiply the exponents. So x squared to the 4th power is x to the 8th. I multiply the exponents. 7 cubed to the 5th power is 7 to the 15th power. I multiply the exponents. If I want to cancel out an exponent, if I want to make this exponent 1, I raise it to the inverse or reciprocal power. So 1/2 times 2 is 1, so that's x to the first, or just x. 1/3 times 3 is x to the first, again, or just x. So that's how we cancel out a fractional exponent. If we have an exponent that is a fraction, and that's all it is, and I need to deal with that, that denominator represents the index on a radical. So this would be square root of x because my denominator is 2. This one would be cube root of x because my denominator is 3. Alright, let's do an example here. We're going to do a couple of examples. Our first example, let's do x to the 2/3 power equals 4. Our second example is going to be x plus 5 to the 2/5 power equals 4. Okay, let's work through this first one. My rational exponent represents, this would be, if I wanted to rewrite it with a radical, I'd say, oh look, there's an x as my denominator, as my base. My denominator is 3, so that's the cube root of, and then I'm going to square it because my numerator is 2. That's what that rational exponent represents without the exponent as the form, radical form instead. But what we want to do is solve for x. So we want to eliminate that exponent. We want to turn it into a 1. So what we're doing is working with that. We want to cancel out an exponent by raising it to the reciprocal power. Well, the reciprocal of 2/3 is 3/2. What I do to one side of my equation, I do to the other. 2 times 3 is 6, 2 times 3 is 6, 6 over 6 is just 1, so we have made this x. We've solved for x. Now we're going to use this principle to evaluate this, 4 to the 3/2. Well, rational exponent, I've got a base of my exponent. It's the radicand, the value under the radical. The denominator gives me the index of my radical. The numerator gives me the power that I need to raise it to. Well, the index is 2, so square root. I don't have to write that there. Could, but I don't need to. And then once I take the square root of 4, I need to raise it to that power of 3. Well, square root of 4 is 2, and 2 cubed is 8. All right. What did I mess up? Anytime I take the square root to solve, I have to remember to consider plus or minus. So that means I've got plus or minus 2 cubed. Positive 2 cubed is 8. Negative 2 cubed is negative 8. So I actually have two solutions there. I have 8 and I have negative 8 as my solutions. Don't forget, when you take the square root, consider both options plus or minus. Don't have to do that if I take the cube root, but if I take the square root, my index is even, I've got to consider both options. All right, let's look over here. We've got, again, a rational exponent. We're going to raise it, both sides of our equation, to the reciprocal power to solve. Well, 10 over 10 is just 1, so the left side of my equation simplifies to x plus 5. Right side of the equation, base raised to a rational exponent, square root of 4, because there's my index. That's going to be raised to the 5th power. This time I'm going to do it right from the beginning. I'm going to remember plus minus. Well, square root of 4 is 2, plus or minus 2. So I've got x plus 5 equals positive or negative 2 raised to the 5th power, which means I have to work two different equations to figure this out. I've got x plus 5 to the equals a negative 2 to the 5th, and I've got x plus 5 equals positive 2 to the 5th. Well, 2 times 2 is 4, times 2 is 8, 16, and then 32. So this is going to be a negative 32. This one's going to be a positive 32. In both cases, I have to subtract 5 to move that 5 over and solve. I didn't square to solve, I took the square root. So I got two solutions. I'm not stressed about one of them being extraneous. There we go. Alright, so that was our second type of equation. We did radical equations, now we've done rational exponents, which are seriously related to our radical equations. Now we've got two left. Equations of quadratic type is our third, and then absolute value equations is going to be what we tackle last. Equations of quadratic type aren't squared, but they follow the same pattern as a squared or quadratic equation. We have to, our first step is going to be to figure out what x would be. We need to decide what expression is repeated. We need to figure out what x would be. And then we use substitution to make it easier to solve. You're going to see, if you happen to go up the calculus sequence, we have equations of quadratic type with our functions, with our trig functions and everything there as well. Alright, keep in mind our general form of our quadratic equation, ax squared plus bx plus c equals 0. We have something that we're interested in. It shows up in our middle term and it shows up squared in our first term. That is an equation of quadratic type. So, for example, I'm going to do a couple here. For example, if I have x to the 4th minus 5x squared plus 4 equals 0. I've got this quadratic form. Right here I have something, an expression, that is repeated and squared here, because x to the 4th is x squared times to the 2nd power. So I have something and then I have that something squared. That's my substitution. I'm going to rewrite my equation using that substitution. That's the term I identified. So I'm going to say, okay, well, that means I've got u squared minus 5 times u plus 4. There's my substitution. This is quadratic and I know what to do with it. I can factor it. U times u is u squared. Same sign, they're both going to be negative. Factors of 4 is either 1 times 4 or 2 times 2. I need them to add up to 5, so I'm going to use the 1 times 4. That gives me u minus 1 equals 0, u minus 4 equals 0, so u is 1, or u is 4. I'm not done. I'm halfway done. My original equation was not in terms of u, it was in terms of x squared. So I need to come down here and I need to undo my substitution. So instead of u, I replace it again with x squared. Instead of u, I have x squared, because those were the original terms of the original equation. Now look, square root property. I have something squared equals a constant. So I consider the square root, don't forget plus minus. I'm going to use my square root property to solve. Square root of x squared is x, square root of 1 is 1, so plus or minus 1. Square root of x squared is x, plus or minus. Square root of 4 is 2, so plus or minus 2. Notice that I got 4 solutions here. I've got positive 1, negative 1, positive 2, negative 2. If I wanted to write those out from least to greatest, they'd look like this, but I don't have to. When I had just a squared function, I had 2 solutions. When I have a 4th degree polynomial, I get 4 solutions. That is a thing that we can continue to expect to see. The degree of our polynomial determines how many total solutions you will have. Okay. Now that looks a little weird if you're thinking of those directions when I give you rational exponents. So let's focus on what happens with this function with rational exponents. Now I see that it looks kind of like my quadratic equation, but it's definitely not second degree. However, if I identify this as my base term, right here, 1/3 squared is 2/3. So I have something, and then I have that something squared, so that gives me my substitution. There's my substitution. So I can rewrite my equation. Instead of x to the 2/3, that's just u squared minus u minus 6 equals 0. Substitution, substitution squared. All right, u squared minus u minus 6, it's quadratic. I can factor it. U times u is u squared. This time my constant's negative, so I have opposite signs, 1 plus 1 minus. Think about factors of 6. Well, 6 is 1 times 6, or 2 times 3. I need the difference, because one's positive, one's negative, to give me a -1. Well, the difference between 2 and 3, that's going to give me 1. And I need it to be a -1, so I'm going to make this a -3 and a +2. -3u, +2u gives me a -1u in the middle. Zero factor property. If I'm multiplying these two factors together and getting 0, then I set them each equal to 0 to see what would make that happen. I get proposed solutions. U equals -2, u equals +3, but I'm not done. My original function was not in terms of u, so I need to come down here and I need to undo that substitution. All right, my substitution was x to the 1/3. X to the 1/3 equals -2. X to the 1/3 equals 3. Now, that's a rational exponent. How do I solve something with a rational exponent? Well, good grief, let's look back over here and see. If I have rational exponents, I raise it to the reciprocal power. The reciprocal of 1/3 is 3. So I'm going to say, all right, I raise both sides to the 3rd power. 1/3 times 3 is just 1, so x is a -8. Right here, x is a 3, 9, 27. You are welcome to use your calculator for those as well. And we can write it x equals, or we can write it in fancy braces. I'm happy either way. Pay attention to what my math lab says. All right, absolute value equations are very last type of equation that we're going to tackle in this section. Remember that an absolute value is a distance from 0 or some central point. I'm going to go ahead and write down from 0. It could be a different value, but it's going to be some central point. So it's always positive. That's the important thing. Absolute value, when you get an answer out of absolute value bars, it's always going to be positive. So let's look at centering things from 0. If I've got a number line, very basic number line, if I leave 0 and I move to the right 1, 2, 3 hops, I'm at +3. If I move from 0, 3 hops to the left, 1, 2, 3 hops, I'm at -3. Both of these values are the same distance from 0. So I would say that the absolute value of 3 is 3. And I would say that the absolute value of -3 is also 3, because that is the distance from 0. Okay? Anything inside the absolute value bars comes out positive. All right, we're going to do 3 examples for this one. So my first example, we've got x minus 2 inside absolute value bars equals 7. My second example, x plus 8 inside absolute value bars equals 3, and then we'll do another one here in a minute. Actually, you know what? Change that one to -3. Let's do that. Okay, so right here. Let's do this one first. Now, since I know that what's going on inside comes out positive, that means that what's going on inside my absolute value bars either started out equal to that +7, or it started out equal to a -7, just like it was 3 or -3 here, and I got the same result when I pulled it out of the absolute value bars. So what's inside is either equal to this or the opposite of that. So I've got two equations to work out. I'm going to add 2 to solve both times. So I get solutions of -5 and 9. Great. Okay. Now let's look at this second one. Absolute value of x plus 8 comes out to be a -3. Does that even work? Well, we just said that whatever comes out of the absolute value bars comes out positive. So there is no value that I will take its absolute value and it will come out negative. That does not exist. D and E does not exist. There is no solution. Another symbol for no solution is that 0. Now, if I chose to change that equation, if I made it x plus 8 absolute value is +3, that one I can solve. I can say, okay, well, x plus 8 equals 3, or x plus 8 equals the opposite of 3, which would be -3. So what's inside, what that x value is, -8, would be either a -5. If I plug in a -5, I get 3. Or x equals -11. If I plug in -11, I get -3, and the absolute value of -3 comes out as +3. So this one doesn't work because of that negative. This one's fine because it's set equal to a +3. All right, real quickly, not super quickly, but one last absolute value equation. Absolute value of a minus 1 equals the absolute value of 2a minus 3. Now this one I wanted to do because we've got two absolute values equal to themselves. We still follow the same principle. We start with what we're given and we say, okay, what's going on over here on the left? A minus 1 is equal to what's going on over here on the right, 2a minus 3, or what's going on the left, a minus 1, is equal to the opposite of, and those parentheses are essential, the opposite of 2a minus 3. Because when I take the opposite of this, I multiply the negative to both of those, not just the 2a. Parentheses are essential. So just like with each of these, we solve two separate equations. We're solving two separate equations, just moving things back and forth. To solve here, I'd like to keep my a's positive, so I'm going to move back to the right. And then I'm going to choose to add 3, so I get a equals 2. Over here, I need to distribute that first. So I've got a minus 1 equals -2a plus 3. Again, I like to keep my a's positive, my variables positive, so I'm going to choose to move the a to the left. And then I need to add that 1 to move it over, and I get 3a equals 4. Well, to finish solving for a, I divide both sides by 3. So I get a equals 4/3. So my solution set here is 4/3